Hello friends, welcome back to the bench. Our patient is a Z170A from MSI. A decent board, nothing special. That is here for a free service of a socket replacement. If you have a board with busted socket, be it 1151, 1200, AM5, doesn't matter, and you have the replacement socket, just ship it over with the replacement socket. I will replace it for free. You only have to pay the return shipping. Now, this is limited time offer, so act fast. Now, I offer this repair for free because there's a difference between knowing how to do something and being proficient at doing something. So I know how to replace the socket, but I'm not quite proficient at it just yet. So I need to gain some experience, and so the best way is to just share your services, help your fellow man. In this video I'm going to show you exactly how to do it. However, be aware that you cannot take my numbers at face value and just replicate it on any other board. Boards are different. Some boards are thicker, some have more copper on them, some have more components, some dissipate heat differently. On some boards I noticed that the solder used has higher melting point than the other ones. I don't know how to tell. It just, once I start doing it and I see that my typical temperature is not moving the socket, I know I have to increase the temperature. So there's no perfect temperature curve that I can give you that you will have the same results every time. But for that, you just need to perform this procedure many times, and you will become proficient to spot when the temperature is too low or too high. Step 1, remove the heat sinks, and as you can see, I left the heat sink on PCH. Typically, the boards you will be working on are going to be expensive boards, obviously, to warrant the repair. So heat sinks on the PCH and perhaps on M.2 slots or somewhere else, they're going to make the board very heavy on this side. So it's probably a good idea to remove it. In this case, it's not very heavy, so also it is screwed in with screws. This part of the board is not gonna get hot, so this is fine. As long as it's not too heavy, you can leave those heat sinks. If on the other hand the heat sink is held by plastic pins with a little spring, it's better to remove it because the plastic might deform ever so slightly from heightened temperature. Why do we remove these heat sinks on VCore and VSA and IO? Well, there are 3 reasons, two out of which I perfectly agree with. The third one we might disagree on, but the first 2 are solid, so the third one is kind of a moot point. Number 1, it obstructs vision and it obstructs the movement of the nozzle across the socket. The boards, again, that you're going to be working on are probably going to have pretty big heat sinks, right, this high. So it's going to obstruct a lot of view and mobility around the socket. It's good to be able to see on all 4 corners to check the alignment right before you start blasting it with temperature. Reason number 2, underneath the heat sinks, there's a pad that is designed to work within the range of temperatures of roughly maybe 60-70 degrees Celsius. The rule in manufacturing is typically that you want it to withstand double the temperature that is expected. So maybe 160, maybe 180 degrees. Not 230 that we're going to be using. So it is safe to assume that the pad is going to deteriorate if you just leave it here. Reason number 3 that we can disagree on, a lot of people suggested to me that my results will be better if I remove the heat sinks, which I didn't do in many previous repairs. I have not seen actual heat sinking effect of the heat sinks. The theory is that the heatsink is going to just pull the temperature of the board and thus reducing the temperature on the socket, making it harder to solder on. I have not observed that. It works pretty much the same with or without heat sinks. A lot of advice that I received often come from people that have either not done this procedure themselves or have done it once or twice and primarily rely on other people suggesting that the heat sinks should be removed for that reason. We can agree that heat sinks should be removed. We might disagree on the reasons why, but as long as we agree that we remove those heat sinks, I think we're good. Step number 2, protect the plastic parts. The memory slots, you're gonna observe that they're gonna start spreading. There's gonna be a lot of temperature. The temperature causes metals and plastics and everything to expand. It's physics, there's no way around it. It doesn't matter how quickly you heat it, how slowly you heat it, how precisely you heat it up. It's always going to expand, it's always going to deform slightly. So memory especially, it might affect the deformation might not go back to the original shape, or the slots might not go back to the original shape, which would cause subtle issues on the memory. The capacitors, they shouldn't explode. The temperature of roughly 220 degrees that we're going to be using, 215, 220, maybe 225, but probably no higher than that. It will not cause the caps to explode. But I have had one board that I exploded the caps. So yeah, they're not going to explode, but they are very close to the temperature, to the maximum temperature at which they do explode. The reason mine exploded is because I moved the nozzle across the cups and they immediately started popping. So they're very close to the temperature of popping, which means they will likely deteriorate slightly if we just treat it with the high temperature like this. For that reason, let's just cover them with aluminum foil. Now I'm using a sticky foil, but a regular aluminum foil that you can buy at the grocery store works perfectly fine. To stick it on, you can use Captain tape, or just stick it somehow, or just place it around the cups. The foil allows you to just kind of wrap it around and it'll hold the shape, so it'll protect the cups. Back to the problem of deformation. Once you start heating it up, and I'll see if I'll be able to show you that, but in case I will not, with my current heater, the board is pretty high up. I can freely look underneath, which I could not do in my previous preheater. And as soon as I get it, as soon as I start the final heating, I can see that the bottom of the board becomes bulged. Again, this is physics, there's no way around it. There's copper inside this board, and once it heats up, it's gonna start expanding. And as it expands, it's gonna change the shape. With these sockets, it's because they have a little window inside, it's less prominent, maybe less concerning than on AM5 sockets, but there's no way around deformation. However, it should, if your temperature is relatively precise and the heating time is relatively short, it should it should go back to its original shape. I've tried it on quite a few boards so far, and after, even though I can see this huge bulge on the back, as soon as the temperature is removed and the procedure is done, it goes back to being nicely flat. For the next steps, we have to set up the station, and I'll show you how I do it. Step 1, obviously, put the board on the holder. Now, since I'm using it upside down, I have an ability to actually screw the board in or screw the board on, right? I can put the little nuts over here, and the board will be very stable. Now, that perhaps if the board is very long and it just tips over like so when you place it on, right? You can mitigate that by removing any heavy equipment from this side, like heat sinks. But if the board is extremely long and it just tips over, then it's a good idea to just screw it on. This is pretty stable, right? It wobbles a bit, but it's pretty stable. Now, it needs to be in the center, but before we put it in the center, for reference, this is not required, because this sensor doesn't really do much other than telling you what the temperature of the board is. But before we align it, let's put the sensor near the socket, as close to the socket as possible, especially for the removal. For the replacement, you don't want it too close so it doesn't stand in the way when you're aligning the socket. The sensor is completely covered by Kapton tape, so it reacts less to the temperature being pushed from the top and more reading the temperature of the board. Relatively close to the socket, I'm actually pretty far from the socket, or pretty far. I'm about maybe 10 millimeters from the socket, maybe a little less, maybe 6-7 millimeters from the socket. So that's a bit far, but when replacing the socket, you might want to put it a little closer, but then again, you don't want it to be in your way. Then we want to align it. We have a nice little scale over here. This is the center. The center needs to be, or the socket needs to be in the center. Now let's tighten the screws. Now, in some cases, if it doesn't work, you perform the whole run and the socket is still solid. And it's solid because the corners are still not melted. Everything inside is floating, but the corners are not. In which case, what I did is I loosened those nuts and just started moving the board across slightly. That definitely produces the result, because the highest heat is in the very center of this heater. But that is also how I exploded 2 cups on one board. So be careful with that. But again, each board is different, especially if you protected the cups with aluminum foil. Even if they explode, they're not gonna hurt you because they're gonna be underneath the foil. They're not gonna splash in your face. And the replacement of those cups is not a big deal. So I've heard someone suggesting that the cups should be removed before this procedure and replaced after the procedure. But that's a lot of added work. If it's not required, I would prefer to avoid that. But it might depend on the value of the board. If those are some very expensive cups that are going to be difficult to replace, or difficult to find a replacement for, very far-fetched but possible, then I guess it would make sense to remove them. Now, the temperature curves. If I didn't forget, You're gonna see my curves on the screen right now. First, I run it on program 0, which preheats the board. So this is the problem I described last time. As soon as I turn on the device, the bottom heater will only turn on when the top heater turns on. There's no way to turn on just the bottom heater. But what I do is I just set 360 on the bottom heater and about maybe 30 degrees on the top heater. Yes, so I set 16 degrees for 500 seconds. That's it. So the top heater shouldn't even get hot, but it does. And since you set it to 16, you shouldn't even feel it getting hot, but it might even burn your finger. We have what we have. It's not the highest precision device that you can get, but it's precise enough to actually get this job done. Once it's preheated, I switch to the program number, I think I have it under 4, which hopefully you can see it on the screen now, the temperature curve that I use. So again, we heat it up to the target temperature, to 15 all the way up to 230. Do not go over 230 or your socket will melt. Not because the socket melts at 230 degrees, it does not. It melts at 260 degrees, but the precision of this heater again is not the highest, so it will melt your socket in some places. And at that point, the socket should be floating. So let's get the tweezers ready. After we remove the socket, we need to clean the pads. That is relatively pain, especially on 1151 and 1200 sockets, because the capacitors are in the middle, so you have to work around them. It's a little painful to perform without actually damaging. You have to work in very uncomfortable positions. You have to burn yourself slightly here and there. You have to burn your tool slightly here and there. So it's kind of a painful procedure, but it has to be done. Otherwise, you're not going to be able to align the socket. For this entire procedure, I do not use flux in any capacity, either for removal or for the replacement. And that is mainly because after you use the flux, or maybe 2 reasons. Reason number 1, the flux burns off before the socket and the board reaches the temperature of melting. So you would have to put the flux right before you're ready to melt it, which you naturally cannot do. Well, it's difficult. Problem number 2, you cannot clean it, and the socket just doesn't look good. You don't want the socket after the replacement to look like it was burned. So no flux whatsoever in my procedure. Feel free to discuss it in the comments below if you have different opinion on it, or if you see that I'm doing something that I could greatly improve. Any criticism is highly appreciated, constructive or otherwise. Okay, let's hit start. Around 10 minutes of preheating should bring the board to about 50-55 degrees. That is all we need. Now, while this is preheating, let me explain, or maybe not explain, because I don't quite get it myself. But we have a switch over here that turns on this fan. This fan blows inward, and you can feel the air coming over here. The air goes around the heater and exits on the edges of the heater. That means that especially working with big BGAs or sockets, the temperature inside is going to be nicely precise, ready, everything's floating, everything's melted, but the edges of the socket are not melted because that airflow. I'm not sure why this fan is here. I mean, I know it's here because naturally the hot air, the heat is gonna travel up, and first this whole thing is getting hot, then here, and all the way up here. Now we have plastic on this side. We don't want it to melt. We have cables and there's some electronics maybe inside, so we don't want to overheat it. That's why this fan is over here, I assume. But when do you turn it on? That is my latest improvement to this procedure. I don't turn it on for the duration of melting the socket, of melting the solder on the socket. As soon as the socket is floating, I remove the socket because it only takes literally seconds. Once you preheat it, it takes maybe a minute, maybe even less than a minute to get the socket off. Then, as soon as the socket is off, I turn on the fan to prevent any damage to the heater. Is that good? I don't know, but it does work. Okay, the preheating stage is done. Our board is roughly at 55 degrees. That's what we want. Now, if it hasn't stopped by itself, I had to restart it a few times because I was leaving and stuff. We're gonna switch to program number 4, which I set to, it grows by 1.83 degrees per second to the temperature of 220 degrees, holds for 200 seconds, and that's the end. So, I'm not turning on the fan yet. I'll turn it on once the socket is off. Lower it all the way, and we'll see if it's not 220. Might be even too big without the fan, but we'll see. Let's start it. 200 seconds. Let's get the light on. So we can see. I am working on a design that will allow me to use the microscope to actually see the balls underneath. That is maybe not necessary for the socket removal, but for the socket replacement, it's crucial to see when the balls started melting. Now, since we have nice good angle on the bottom of the board, we will be able to see how it bulges up or bulges down. There's gonna be a big bubble right behind the socket. Now let's observe the temperature. You can see that it's growing very rapidly. During the preheating stage, you will notice that there is a smell coming from the board. This is normal. You don't want to see the smoke. Well, if you do see the smoke, that might happen when it's especially dirty from some kind of oily substances, some dust, some stuff. There's always going to be some smell when you're preheating the board, so don't be alarmed. But if there's a smoke, it's either, well, during preheating, you're not preheating to the temperature that would actually melt anything or burn anything, but if there is smoke, then there's just too much gunk on it. So it's a good idea if the board is especially dirty to clean it. Probably ultrasonic cleaner would be the best if you have a ultrasonic cleaner big enough to actually accommodate the entire board. Otherwise, just spray it with alcohol, some brush, and clean it that way. We are at 219. No movement from the socket just yet. The board is bulging up. We had a little puff of smoke. We have a first movement from the socket. It's melting. Not the socket, the solder is melting, and the socket is off. Almost. It's holding in the corner, that corner. Okay, it turned off. The socket has melted, or this solder has melted, but it's holding in one corner. So I just moved the board a little closer to give a little more temperature to that corner. That is unfortunately something that will happen. I'm not sure why, but typically it's that corner. On this machine, it's always that corner that it melts last. There. Now, did we pull the pin or the pad? Nope. It looks good. Okay. Did I stop it? I did stop it, and I turned on the fan. So this stage is done. Now the hardest part, clean the solder. Okay, socket is prepped. Now, to make this process easier, you will notice many other technicians first apply a leaded solder to mix with lead-free solder that is on the pins originally, and that lowers the melting temperature, making it easier. As you can see, I don't do it. What I do instead is I use two different kinds of flux. I use the crappy NC flux from MTech, and final touch is Kingbo RMA flux 218. On top of that, I periodically turn on the preheater and the top heater to keep the board temperature high. If the wick caught the board and I can't dislodge it using the soldering iron, I just turn on the heater, and that brings pretty good results. Now, as you can see, the board came back to its original position, right? It's not deformed at this point. The bulging on in the back is gone. This is what we want to see. If you move your finger across the pins, you don't want to feel any, you want to feel pretty much the smooth surface. The other good method is using paper towel when you clean it, and the pieces of paper towel are being caught somewhere there. That means it's not clean. It is time consuming for sure, but you know, the better you prep this stage, the easier it'll be to align the socket. Now let's move to the next step, actually aligning the socket. Now for the alignment, this is what I struggle with the most, and I don't really have a trick to do it. It's what I do is I take a picture before I remove the socket so I can reference it, and then just try to align it as much as well as you can, and hope that it will jump into position once it gets hot. Okay, this looks aligned enough. All we can do is just hope that it is aligned. Now the rest is pretty simple. We just use the same procedure. Preheating. Let's switch to number 0. Start preheating. Now I moved the board again a little closer to me because for some reason that part never gets soldered on entirely. Okay, preheating is more or less done. The board is roughly at 55, 54 at the moment. So let's drop the nozzle without disturbing the board so the socket doesn't move all the way down. And now at this stage, that's why I'm working on the device that will allow me to see from the side, because the socket actually is not flush on the board. It's sitting on the balls, so you can see, you can tell when it dropped on each corner, and once it drops on each corner, you know it's soldered. The fan is off. Let's stop the preheating, switch to program number 4, and 200 seconds of high temperature. One corner already dropped at 190, which is weird, or maybe it's because of flexing. We have some smoke here and there. Some of it is from the Captain tape. Some of it is gonna be from some flux residue. Yeah. Oh, it actually smells like burnt plastic. Oh, the socket melted. The socket has melted. See, different sockets behave differently. And we didn't even reach the target temperature. That sucks. Well, the solder melted here and there. Did we we stop it? We did. Okay. Good thing I lifted it, because it did smell like burnt plastic. Which is weird, because this one did not melt, and the replacement did. Unfortunately, this was my last socket. I actually didn't even know. I thought I had one more box of these. I need to order some more, and I have to hustle before the tariffs hit, because they're going to be twice as expensive if once the tariffs hit. Anyways, this is one of the challenges. It not only melted, it deformed completely. Too bad I didn't catch it in time. The challenge is that you never know what kind of socket you will get. So when you order these, just order 10 at a time, so you can ruin one of them and know what to do with the remaining 9. Unfortunately, I did not know this was a leaded solder socket. The solder started melting in multiple places when we hit around roughly 190 degrees. So this particular socket should be resoldered probably at 170, 180. Probably 180 is the max. So this one is ruined, but nothing happened to the board. I cleaned the solder that has melted, and it's ready for another socket. Unfortunately, not in stock. So on second thought, if you're sending the board with a socket, just send it with 2 sockets just in case. Because remember, the free service comes with no guarantee, and some sockets I can test, like 1151, because I have CPUs, but if you're sending AM5, I have no way of testing it. But AM5, they require different temperatures, and the procedure is slightly different, but for the most part it's the same thing. The general idea is the same. Well, hopefully you found this failure useful. The procedure as I described still stands. It is that's how you replace the socket. We have no permanent warping of the board, and actually with the socket that comes with leaded solder like this one, since we're only heating it up to about maybe 180, maybe 170, 175, something like that, 165 perhaps, the board is not going to experience as much flexing, and that is pretty important, because once the board flexes, it bulges up. Then the solder balls might not solder on correctly. They might be dangling, and then when the board returns to its original position, some solder balls are not actually connecting to the board. So that is the challenge, and unfortunately you can't see that inside. You can see the balls on the edges, sure, but you can't see that on inside. And I should have stopped heating as soon as I noticed that one of the corners dropped. That was way too quickly, because we didn't even get to, we barely got to 190 and it already dropped. I should have known then that this is going to be leaded solder, not lead free. Well, you can't win them all, but the board is still going to be fixed as soon as I get the replacement sockets, which I'm going to order right now. In any case, thank you guys very much for watching. I do appreciate you, and I shall see you in the next one.